the next proposition. The field axioms imply the following statements for any x, y, z in the field. A. 0 times x equals 0. It means the product of the additive identity element with any element in the field x gives the additive identity element 0. B. If x is not equals to 0 and y is not equals to 0, then the product xy is also not equals to 0. C. The product of the additive inverse of x with y is exactly same as the additive inverse of the product xy, or it is equal to the product of the element x with the additive inverse of y. D. The product of the additive inverses of x and y is exactly equal to the product xy. Let's have a look at the proof of the statement 1. So we begin with the statement that 0x plus 0x equals 0 plus 0 times x. This is the distributive law for the field. And then 0 plus 0 can be replaced by 0 here, because it is the definition. And then, since this is the field element by the axiom M1, any field element can be replaced by the field element plus 0. So we have 0x plus 0x in the left hand side and 0x plus 0 in the right hand side. By the cancellation law for addition we proved earlier, we obtained a statement that 0x equals 0. This is the end of the proof of the statement A. Let's try to prove the statement B, which says if x is not 0 and y is not 0, then the product is also not equal to 0. We'll prove this by the method of contradiction. Suppose on the contrary that the product is equal to 0. Then we can begin with the statement. Y can be written as 1 times y. This is the definition of the element 1. And then 1 can be replaced by the product x inverse x. And then by the associative law for multiplication, we can write this statement like this way, x inverse times xy. By the hypothesis, xy is 0. Then in A, we just proved that any field element multiplied with 0 gives us 0. So this gives us that y equals 0. But this contradicts our hypothesis that y was not equal to 0. So our assumption here was wrong. And this contradiction proves the assertion. Similarly, you can try to prove the rest. Ordered field. An ordered field is a field which is also an ordered set, such that if x, y, and z are in F and y is smaller than z, then x plus y is also smaller than x plus z. 2. If x is in F and y is in F and x and y are both positive, then the product is also positive. In particular, the statement 1 implies that if x is negative y, then the left hand side becomes 0 and the right hand side becomes negative y plus z. And by the commutative law for addition makes this statement. So if y is less than z, we can write z minus y is positive. So one implies the other. For example, Q is an ordered field, but the complex field C is not an ordered field. Proposition: the following statements are true for every ordered field. Namely, if x is positive, then the negative x is negative, and vice versa. Means if negative x is negative, then x must be positive. If x is positive and y is smaller than z, then xy must be also smaller than xz. So this can be memorized or remembered this way. If y is smaller than z and x is any positive filled element, then we can multiply both sides by x. Similarly, if x is negative and y is smaller than z, then the product xy is greater than the product xz. So note here, if x is negative and y is smaller than z, the left hand side now gets bigger than the right hand side. This is true for rationals, but now we are saying that this is also true for any ordered field. D. If x is not equal to 0, then x squared must be positive. In particular, 1 is bigger than 0. In the field axioms, it was not clear whether 1 is bigger or smaller than 0. We assumed that 1 was not equal to 0. But in D, now we will confirm that 1 must be greater than 0. The multiplicative identity is greater than the additive identity element. The statement E reads, if y is bigger than x, bigger than 0, then their multiplicative inverses reverse in order. Means the multiplicative inverse of y becomes smaller than the multiplicative inverse of x, but both remain positive. So bigger the filled element, smaller the multiplicative inverse. Let's try to prove the statement A. We have x is positive, and then by applying the property of the ordered field 1, if y is smaller than z, then x plus y is smaller than x plus z. By assuming y here is 0 and z here is x, we can add any element to both sides. Namely, we are going to add negative x. So this is negative x we are adding to both sides of this inequality, assuming that this is y and this is z. So the left hand side gives, by definition of the additive identity element, any element, filled element, plus the 0 is the element itself, and the right hand side gives the 0 by definition of the additive inverse of an element. So we are done. If x is positive, its negative is smaller than 0. Similarly, we can prove the statement B. Please pause the video and try to read the proof. Let's try to prove the statement D. Namely, if x is not 0, then x squared must be larger than 0. In particular, 1 is larger than 0. So if x is positive, then by b, considering y as 0 and z equals to x, we obtain x squared larger than 0. If x is negative, then by c, with y equals x and z equals 0, we obtain also the statement that x squared is larger than 0. In particular, since 1 is not equal to 0 by the assumption in the field axiom, then we can use the statement that 1 times 1 should be larger than 0. But we also saw that 1 times 1 is equal to 1. This confirms that the multiplicative identity element in a field is greater than the additive identity element in the field. Similarly, we can try to prove the statement E. Namely, if y is bigger than x, bigger than 0, then their multiplicative inverses satisfy this relation. So, bigger the field element, smaller the multiplicative inverse. In order to show that, we first want to prove that if x is positive, then its multiplicative inverse is also positive. And this is true for every element in the field. Suppose on the contrary that the multiplicative inverse of an element x is negative. Then by b, with y equals x inverse and z equals 0, we obtain this statement, which gives that 1 is smaller than 0, which contradicts the statement D. This contradiction proves that if x is positive, then its multiplicative inverse is also positive. Now please pause the video and try to read the rest of the proof. The real field. We now state the existence theorem for the real field R without proof. The proof actually constructs the field R from the field of rational numbers. Theorem. There exists an ordered field R which has the list upper bound property. Moreover, the field R contains the field of rational numbers as a subfield. In other words, every non-empty subset of R that is bounded above has a supremum in R. So R is complete in the sense of having the list upper bounds of every non-empty bounded above subset of it. So this property is known as the supremum or list upper bound property of R. An element of this new field R is called a real number. If alpha is in R but it is not in the Q, then it is called an irrational number. Like square root of 2 was not in Q, but we know by definition that square root of 2 is the list upper bound property of a set E of rational such that R is positive and square is smaller than 2. So this number is the supremum of the set, which doesn't exist in Q but exists in the new field R. So this number is called an irrational number. Now we have the formal definition of an irrational number. Any element in R is not in Q is called an irrational number. With this supremum property of R, we can prove that for every positive element in R, there exists an element alpha in R such that alpha squared equals y. Then this alpha is called a positive square root of y, denoted by this symbol, the radical symbol. So this example, with the help of supremum property of R, guarantees that every positive number y has a positive square root. This is the existence theorem for the positive square root.